once you will be seeing yourself, which will be a delay. So we'll start.
Yeah. Hello and welcome to this session, for this live session for the NPTEL course on Introduction to Operating Systems. Some of you, I hope you are enjoying the course so far. Some of you have actually raised a few questions. So we'll actually start this live session by actually looking at those questions. And after that, you'll be please feel free to actually ask me any question or any concerns that you actually have. So there are a couple of questions. Many of them are related to the assignments that we've had. So the first was by a student called Pani Ratan, whose question was, does this course help me in the lab for component system programming in C? Okay, so essentially this particular course is very relevant to essentially if you want to understand systems, because it gives you the fundamentals over which all all applications are built. Now specifically, if you are looking at, I'm not very certain what is this component system programming, but essentially if you're writing any system level programs, anything at with C level, and you want to actually understand what is actually happening in your applications, then this particular course would actually be very useful. So the second part of the question is about the scheduling algorithms. And if you can explain the scheduling algorithms using codes. So in fact, so in this particular course, as such, since we wanted to keep it at an introductory level, so I've actually abstracted the scheduling algorithms. So I did not go into too much detail because of how the scheduling algorithm works, just because it may not fit into these into the syllabus of this particular course. So therefore, what I could actually mention to you is that scheduling is of course a very interesting topic. There are a lot of scheduling algorithms. Some of them we've actually looked at in the course, but also one very interesting aspect is about the context switching, which is part of every scheduling algorithm. So if you are actually interested to learn more about these scheduling algorithms, I would suggest that you start off with looking at the code. You can either start, if you're very well versed with an operating system like Linux and you have very strong C coding skills, then I would actually suggest that you look into the Linux kernel and you could open the scheduler code.
One question, you can answer it.
Okay. You could open the scheduler. If you are not very comfortable with the Linux kernel and C programming, and rather you actually want something very concise and small, so you could actually look at XV6. The XV6 source code has a very small and simple round robin scheduler, and in particular it has the context switch. So I would actually request you to look into the XV6 source code to actually get a better idea about how scheduling algorithms work internally and how they're actually programmed. Okay, the second question is from Anurekha, who's a faculty. So this was mostly about the assignments. She has very rightly found out that in one assignment the answer should have been 5, but we have actually put the wrong, none of the choices were matching. So we've actually made that correction, and we have taken this into consideration while actually grading. Now she also found that some other questions relating to the assignment, which, so in case you like by chance there are we try as far as possible to validate all the questions, but she has also found out that there is this one question which has 2 right answers, in which case we would give credit to both answers. So a question from Raja Rajan, who is a faculty. So his question is, let us say that you have a 32-bit machine, and therefore the maximum addressable range is 2 power 32. Okay, so assuming that there is 4 GB of RAM, which is the maximum addressable range, so he wants to know how you could actually increase to 5 GB. So if I understand the question properly, he says that, for example, let us say if you have a 5 GB RAM, but you have a 32-bit machine, can you access the entire 5 GB? So this is a very interesting question, because the size of your address bus essentially limits the amount of RAM that you can have. So if you are having 4 GB, if you're having 4 GB RAM, you on a 32-bit machine, this is the maximum of RAM that you can have. So for example, if you have, let's say, 8 GB of RAM, but you're running a 32-bit operating system, you will be only able to use, under normal circumstances, you'll be only able to use the lower 4 GB, that is from 0th address to 8 Fs. So there is a thing about they can't hear you. The question that you can't hear. So it essentially means that the whether you're doing a 32-bit machine, your maximum RAM that you can have is 4 GB, so you can never extend it under normal circumstances. On the other hand, there are some techniques that will allow you to actually use higher amount of RAM on a 32-bit machine, but these do not actually fall directly into the operating system perspective. You would have special drivers which will make use of actually mapping these higher RAM into this lower region. Okay. There are a couple of questions by Krishna Kant. One question is about the bounded weight. So as we know that there are 3 criteria for the critical section, and one of them is the bounded weight. So his question essentially is that if I have a process which is in a critical section and it is actually copying 100 GB of data from, say, one hard disk or one file to another, then isn't that a bounded weight problem? So the bounded weight is actually the definition of bounded weight is very subtle. So what it means is that suppose a process is waiting to enter the critical section, right? There should be a finite amount of time there should be a finite amount of time for which this process should actually be waiting. So what do we define by this finite? So as Krishna Kant has rightly pointed out, the finite time, how do you quantify this finite time? So finite time, for example, could be something from a few milliseconds to seconds or hours as well. So typically what we do in this particular scenario is we actually define bounded weight as something like this, right? So suppose one of the process is waiting for to enter the critical section, and you have multiple processes, other processes which have been able to get the lock and are being able to actually enter into the critical section, right? So for example, I have 2 processes. One is waiting on the critical section, while the other process, due to some reason, has been able to enter in and leave the critical section multiple times. So this is a bounded wait. So it's some kind of a...
Wait a minute. Can I remove this?
Yeah, sure.
It isn't that the photo is copied?
I don't think it's needed anyway, so you can...
Not needed. I think the power is consuming too much. So this audio is getting disconnected often.
Oh, okay.
I can hear.
Yeah.
Exit.
Then keep on.
Okay. So sorry for the for that interruption. So we are having some audio problems. So there is also a concern about from Krishna Khan that some of his questions have not been answered. So while we actually try to answer most of the questions, there may be a few which please also note that we actually get a lot of email since there are a large number of students answering taking the course. So there may be a few questions which may actually be skipped, but I assure you that it's not intentional. Gayatri is a student, so she wants to know what is the textbook to be followed for operating systems. So as such, I have not followed any specific textbook. So what I did try to do was just follow the code, and at least for the first part of the course, I tried to actually follow the code of XV6 and the documents available online for the XV6 operating system. The textbooks which I did follow was mostly for the later part, which is for the process synchronization. So that was a combination of Galvin as well as the Stallings textbook. I think even the Tannenbaum as well. So I would suggest that if you want to actually use a textbook for operating systems, there is no single textbook which will actually help you. So that you can use a standard textbook, but try to actually get information from all of them, and try some topics are better explained in one textbook, while other topics are more better explained in another textbook. So whichever actually suits you, and you should be actually following. So ideally you could actually read a few sections for each chapter based on whichever textbook is explaining that better. Finally, there is a question from Nagashwati. So it is more about so her question is more about C programming, so it is not in context over here. I would suggest that you could actually look up any C book. The most famous, of course, is the Kernel and Ritchie. The pointers in C is also good, but you could actually use that to like if you have any C queries. So in this particular course, we will assume that you have a good knowledge of C, and we will actually start with that assumption. Okay. Okay, so there is a question from Varun Kumar, who asks about videos for kernel debugging. So as I did mention earlier, so this particular course is an introductory course for operating systems. In the future, we will actually try to have a more advanced course where we look at say for example the Linux kernel in more detail, and we will actually see how you'd probably do debugging in that kernel, and use techniques like GDB and things like that to do kernel level debugging. So this would of course be in a future course, but it's not covered in this particular course. So what are the major research scopes in operating systems? So operating system research, it has been evolving for like several decades now, and over the years there have been many features which have been incorporated in operating systems, and also over the years the objective of the research has been changing. So for example, in the early 2000s, 2000 to 2009 or so, the focus of operating system research was actually to reduce the energy constraints. So you would, for example, find scheduling algorithms which would actually reduce the energy consumption of your entire device. And as you would likely have guessed, these operating systems were more targeted for battery operated devices like mobile phones or any of the IoT kind of networks. IoT kind of devices. More recently, there has been stress for operating systems to have increased security. So there have been various different variants. You have operating systems which have been designed by Google to make things more lighter and also more secure. So there have been things, aspects to have a capability based operating system, more from a university perspective. There have been things about separation kernels and so on. So while operating system is a very established topic for research, and the focus has been changing over the years, and yeah, it's possibly something you would always find scope to do some exciting research. So one thing which actually is exciting with respect to operating systems research is that this is one layer of software which directly communicates with the hardware. So you could modify the operating system by a few lines and it could actually change the entire way your system functions. Just to give an example, if you could actually say modify the scheduling algorithm in your operating system, and you'd actually find that the way your entire system functions would look or would be very different from the normal operation. So are there any other questions? So if you have any other questions, then you can just ask it now. So there is a question from Vinutha about how to find the schedule length. So Vinutha, could you actually explain what do you mean by schedule length? Because schedule length is not a conventional term we use in operating systems. So if you can expand on that, then it would be easier for us to answer the question. So are there any specific questions that you would like to ask? You can just post it now and then we can try to answer those questions. So in assignment 5, so we'll go over this question, assignment 5 question 4. So you can just go into that third screen. Yeah, not this.
This one.
No, not this one, the other one, the assignments. Okay, how you can define the OS by, so education, yeah, so we'll just take this, this one, this NPTEL. Assignment 5 question 4. Scheduling. So the fourth question over here is about the first come first serve scheduler. Sorry, question 3. Each person. Okay. For the process, schedule length. Okay. Oh, okay. Scheduler length. Thing is not being, the length of scheduling. So yeah, so in this particular thing, this particular question, so what you want to do is to actually identify the yeah, you can just close this and go back. Yeah. So in this particular question, what you actually want to do is to identify the scheduler length. So what is meant over here is that you want to identify for these particular processes given over here, what is the burst time, or what is the total time the scheduler executes and is able to schedule these various programs for the given burst times. So educational bytes ask a question about how you can define OS by the need of hardware. Could educational bytes, can you actually elaborate on that particular question? What do you mean by, what is meant by defining an OS by the need of hardware? Oh, okay. So if I will answer something now about what I feel, but if I'm not answering your question, please ask it again. Please rephrase the question and ask it again. So what I think you are trying to ask is, given a particular hardware, how should the operating system be designed? So you see that every operating system, or rather every system that we develop, is eventually designed for a particular application. So you could have operating system, or you could have systems that are designed, say, for a mobile phone. You could have systems designed for, say, a desktop or some user-based thing. You could have systems which are designed, let us say, for computer games. On the other hand, you could have systems which are designed for, let us say, a high-end cloud computing environment. So each of these things have very different objectives. So while at one point in the OS for the mobile phone, you would actually want to reduce the priorities for applications which are, say, running at the background, and give maximum priority to the application which is currently active, right? So the scheduler in such cases would actually be different. Similarly, you would actually want to have very strict energy conservations and techniques, especially for the various devices like Bluetooth or the flash and so on. And therefore, for example, you would want your operating system to be able to turn off or be able to operate these various devices so that the minimal amount of power gets consumed. If you take the other extreme of let us say a cloud computing environment, let us say like in an Amazon cloud, so in such cases you want your scheduler to be fair to all applications which are running on this on the particular cloud. So in a cloud computing environment, for example, a server would be required to be fair to all of these users who are actually connected to that particular system. Furthermore, you would actually want very low latency for interacting with the secondary storage device or with the various disk or any other storage device that is present, so that your performance is actually boosted. So the operating system design is then also affected in such cases. So the in a high-end server, you may actually want a fair scheduling policy in your scheduler, so which is very different from what you would actually see in your in a typical mobile phone. So furthermore, you would also want to have highly efficient file systems. You don't mind actually spending more time on caching data, for example, in the OS, so that the file system latencies are actually reduced. A third aspect, for example, you may also take is say a real-time system. For example, an operating system that is used in an automobile or any other control industry. So in such a case, what you would actually see is that you want to actually give priority for the highest, for the most critical tasks, while lower the priority for other tasks. So in such systems, for example, you want them to be highly deterministic. So you would, for example, disable the use of the memory management unit. Therefore, you would assume that no page faults can ever occur. And a limitation for this obviously is that you want the entire OS and all the applications to be persistently present on the RAM. You cannot actually be able to swap in and swap out pages as is typically done in all other scenarios. So while this assumes that it doesn't give you the luxury to have very large programs, but it would actually ensure better determinism, that no the asynchronous page faults can occur, and your timing behavior is more better predictable. Rishabh Jain has asked about the current research trends in operating systems. So while I am guessing that there are multiple different perspectives about or different aspects about operating systems, you could have operating systems to support the various new memory architectures which are present on your systems. There are, for example, OS support for the new memory devices that are being designed, like NVM, non-volatile memories, and so on. What we, at least the perspective which I am looking at, is more from a security perspective, where we also look at, or rather we look at being able to improve the security of operating systems. So we actually look at things by which we could actually add features into the operating system which would boost the security of your entire system. As you know that the OS is a fundamental layer between the hardware and the applications. So while most hardware cannot be modified once it has been designed, the operating system can be in fact changed, essentially because it's all software, and therefore it would actually permit you to actually change the OS, add more security features to get a much more rugged and secure system. I hope this answers, at least addresses some of your questions, Rishabh. If you have any specific research direction you are interested in, then you could always let me know by email. So there are there any more questions? Thrashing. Okay, there's another question from Educational Bytes on how do you define thrashing. Yeah, so page thrashing could occur when you have repeated page falls. You have a large number of swapping in and swapping out of memory from between the RAM and the corresponding hard disk or secondary storage device. So the thrashing could actually increase the or actually reduce the performance of your system, because the increased number of page falls would cause the page fault handler to get executed a large number of times and cause data to be actually swapped in and swapped out from your secondary storage device to your memory and vice versa. So while one easy way to actually reduce thrashing is to actually increase the amount of RAM present in your system. The other alternative would be to have, while you're designing the operating system, you ensure that you have a very good page replacement policy such that thrashing can be eliminated. Or you cannot eliminate thrashing, but at least you can reduce the chances that thrashing actually occurs. So Selvi has a question about threads. So threads, as we've seen in one of these video lectures, so they are essentially lightweight processes. There are like various types of threads. You could have user level threads, kernel level threads, and so on. Now, essentially the difference between a process and a thread is that a thread shares the context with the process. So each thread that you actually spawn out would have a different stack, but would actually share the other segments of code, heap, and so on with the main process. So for example, if I have one process and in that process I actually spawn, say, multiple threads, all of those threads would be able to actually access the same code and global data and heap, which is common to of that particular process. On the other hand, each of these threads has its own stack, right? So as we've seen in the last lecture, every program has a stack. So in this particular case, if you have multiple threads, it's the fact that each thread in the process would have its own stack. So this way each thread could actually run in its own context. It could call functions, it could be scheduled in the processor, and it would be able to actually execute things in parallel. Each thread could actually execute a function asynchronously with respect to the other threads. While the main advantage of threading is that you're able to parallelize your workload, while one system, for example, is waiting for, say, a disk operation to complete, or a user to actually give an input, another thread could actually be executing during that particular time. So there are certain applications where multi-threading would actually benefit quite a bit. So all of this, what I actually mentioned, could also be possible with processes. However, processes are much more heavy. You could, for example, have an application which is split into 5 processes. Now, each of these 5 processes would have a separate virtual space. They would have separate code, data, stack, and heap, and all of them are independent. So this means that you're actually going to take up more space of physical memory. The context, to save the context, would be much higher in the kernel, and also communicating between these various processes would be much more overheads. If you have a multi-threaded application, since there are these 2 threads sharing the same process's virtual address space, so the best way and the most easy way to actually communicate between these 2 threads is to just have a global object, and let these 2 threads actually access this object. On the other hand, if you want to actually achieve the same thing with 2 processes with their own virtual address space, so you would actually require to create a shared memory or pipes or any other IPC mechanism to actually communicate between these 2 processes. So is there any other question? So Sandeep Pandey has actually had this very interesting question about how can you build our own OS. So this is a very interesting question because I feel that if somebody is actually interested in understanding an operating system thoroughly, just using the textbooks would not be a solution, or just reading the textbooks or any number of textbooks you read is not going to be the solution. So best way to understand an operating system completely is to be able to actually build it. So luckily for us, there are several toy operating systems which are actually meant for this purpose. So I would we follow, for example, in this course, at least we've been trying to look at the XV6 operating system from the MIT. So if you actually go to the MIT website, there is also some pages about the corresponding lab. So this lab, in fact, works on something known as a JOS or JOS operating system. So this this essentially is a series of around 10 or less than 10 assignments, starting from assignment 1 where you actually boot up a system, assignment 2 where you actually initialize various memory and other aspects in the system, and so on. So if you're able to actually follow all of these assignments from assignment 1 towards the end, maybe at least 4 of assignment 5, you would be actually able to get your own operating system running. So if you look at these assignments, each assignment comes with very detailed procedure about what are the steps involved, what you need to actually fill in, what you actually need to find out, and it also gives you small pieces of code which would help you to understand what is actually going on in the operating system. And there are small questions as to like, for example, to be able to fill certain lines of code which are incomplete. So Sandeep, I would suggest that you actually look at XV6 website, look in particular at the labs present over there, and start from the assignment 1 where the setup is actually created. And if you actually are able to do up to, say, assignment 4 or 5, you can be assured that you actually have a very simple operating system of your own which can run and actually boot up on an emulator. So yeah, I would be happy to help you if you actually get stuck in any of these things. So you can always send an email to me. So Giridhar Kumar has a question about semaphores and mutex. Essentially he wants to know what is the difference between a semaphore and a mutex. So mutex, as the textbooks say, is a binary semaphore. So what it means is just has one bit of information. So it can have a value of either true or false. So if there are if you have one resource and this resource is shared among, say, multiple processes or multiple threads, then you use a mutex. So what the mutex would guarantee is that exactly one so what the mutex would actually guarantee is that exactly one of these processes has access to the shared object at a particular time. So this is a mutex. Now when you come to a semaphore, we take an example. Let us say that you have actually 5 such objects, right? And let us say you have multiple processes which want to access any of these 5 objects. Say you have 5 objects and 10 processes, and the requirement is that each process should access any of these 5 objects. So obviously if there are just 5 processes and 5 objects, we would not have a problem, because each process would be allocated one object, and there is no locking mechanism that is required. On the other hand, if we now consider the larger number of objects, larger number of processes, 10 processes and a smaller number of objects, then we need a locking mechanism. Now in this particular case, a mutex would not be useful, but rather a semaphore would actually be a better solution. What the semaphore would be actually guarantee is that any process would be allocated any of these 5 objects, shared objects. So in this particular case, we would initialize the semaphore to a value of 5, and it would keep decrementing corresponding to the number of processes having access to the object. So at any instant, for example, over here, it is guaranteed by the semaphore that exactly 5 or at most 5 processes have access to the object. So Sandeep Pandey has another question. Please provide a dedicated video on that, or at least provide the link on the forum. So I can actually share. We can actually share the link to the XV6 website. I think it's already been shared, but we can actually give it to you again. And in particular, we'll also share the one on the JAWS operating system, and also the assignments which are present in the MIT's website for XV6, which will permit you to actually build your own operating system. Sandeep has another question about how can we start building our own OS using the Linux kernel. Okay, so I do not understand this question properly, because if you have a Linux kernel, then you already have an operating system. What I do understand is, what I do think you're trying to ask is whether how would you actually use the Linux kernel and then build your own system out of that. So this is not very difficult. This is not very difficult to do. So there are loads of tutorials which would let you build a kernel and compile a kernel right up from scratch. So in fact, there are a couple of distributions also which would let you to actually build kernels from scratch, and then add various applications and customize your kernel and your system as per requirement. Okay. Madhuri has a question about threads and deadlocks. So she actually asks whether there is any relationship between threads and deadlocks. So essentially, as we seen in the deadlock class, we have like multiple processes, and there are certain criteria of if a certain criteria happens, like a circular weight and so on, then a deadlock can occur. But this is not restricted to only processes. So even if you have one process which has multiple threads, and all of these the deadlock criteria are met, then a deadlock can occur. So in summary, it's not just deadlocks occur due to processes only, but threads can also get into a deadlock situation. So Krishnakant has asked a question about pthreads. So why do you need pthread join, and why do you use pthread exit? So pthread exit for pthread join is used in the parent thread. So when you fork a thread, you actually invoke pthread join. So for example, I could take one of these slides. I can just go to screen 2. Process management. So I don't have this. Threading is not there. So So as we see over here, Krishnakant, that we have a pthread exit, which is essentially used to exit a thread. On the other hand, pthread join just previous slide. So pthread join, for example, is used over here. It is used in the parent thread to essentially wait till the child thread or the thread that has been created has exited. So for example, in this particular program, although we don't use an explicit pthread exit, it gives you a notion of how we use pthread create and pthread join. So pthread create over here, for example, tells you that you want to start a thread which executes this thread function. The way you actually specify this is by giving a function over here known as thread function. So it means that a thread gets created in this process which is going to execute this particular function. So this particular process would have totally 3 threads. It has the main thread, which is corresponding to this main function. It has 2 threads, T1 and T2, which are executing this particular function known as thread function. So each of these 2 threads would essentially just start, sleep for some time, and then exit. Now, while it is sleeping, the main thread invokes this pthread join. So pthread join over here essentially causes this main thread to block until, in this case, thread 1 exits, and then over here thread 2 exits. So I hope this actually helps you, helps answer your question. So this particular thing does not, this particular program does not have pthread exit, but it would be implicitly called in this thread function. Okay, so Selvi has a question about concurrency and parallelism. No, this one only. No, same thing. This, yeah, same slides. Yeah. So, So her question again is about threads. So I'll answer that question again with respect to this particular program. So Selvi, as you see, as we explained previously, we have 3 threads over here. Now let us assume that we are running this particular program on a machine with 4 cores. So what is going to happen in such a case, most typically, is that let us say core 1 actually runs the main thread. That is, this particular program starts to execute from core 1. So when Pthread gets created, the operating system is going to allocate another core for it, say core 2. And when the second thread T2 gets created, the operating system is going to allocate, let's say, for example, core 3 for the second thread. So therefore, we have parallelism over here. Concurrently, we have the same process executing on 3 different cores of the CPU. Each core is running a different thread. Core 1 runs the main thread, and core 2 and 3 runs the thread function. So this actually gives you the parallelism. In this toy example over here, we do not have any shared variables, or all the threads are kind of independent. So we do not have to worry too much about any kind of synchronization. However, if, for example, we had a shared variable in this particular program, which is shared across these, say, 2 threads which are created, these 2 child threads, then you would have to use either some form of mutex or semaphore or any other synchronization mechanism to ensure synchronization between the various threads. Selvi, I hope this answers your question. So Jaya Karthi asks, so why Jaya Karthi asks, why is thread called a lightweight process? Okay, so if you actually look at a process, so you can just go back. Okay, no, same thing. Sorry. Where is it? Go down. Down. Yeah, let's go back. So so the question over here is, why is threads called a lightweight process? So I've actually taken this particular slide from processes, and this shows the address space for a single process. So as we know that each process has some text section, which is essentially has the instructions and code. Then it has a data section, it has stack, and it has heap, and each process also has a kernel stack. In addition to this, just go down. Next. In addition to this, there is a context for the process. In x86, this is known. This is actually stored in the kernel, in the structure known as struct proc. And as we see over here, there are many things which are actually present, like the files open, current working directory, executable name, and kernel stack pointer, and so on. Now, these are for processes. Now, when it comes to threads, right? Threads are called lightweight because a lot of these structures are actually taken from the parent thread. For example, in the example that we've seen before, we have this main process, the main thread, and the 2 child threads. So the child threads essentially share a lot of these structure entries with that of the parent thread. For example, it would share the entry of the files open. It would share the current working directory, the executable name, and so on. In some operating systems, it would also share the same trap frame. It would share the same PID, and so on. If you just go back 2 slides, previous thing, yeah. So now in a multi-threaded program, because of all of these shared things, if I have this particular process and I have, say, this is one process, and if I have multiple threads in this particular process, the virtual address space for all of those threads is actually shared, and as shown over here. So all of these threads would have the same data, same code, which is the text section. It would have the same data, and it would have the same heap. The only thing that would be distinguish all of these 10 threads in the single process is that each of these threads would have a different stack. Now, in some operating systems, it is likely that this one process, all the threads within the single process also share the same kernel stack. However, in Linux, each thread in this process is given a different kernel stack. So I hope this shows how, so because of a lot of data or a lot of things which are actually shared with the parent process and shared between all threads within a process, we actually consider threads as lightweight. It is called as a process because essentially it is an independent executing environment. It gets executed, gets picked up by the scheduler, it gets CPU time and executes in the CPU. So I hope this answers your questions, and also Smita's question, who is in a who is kind of a similar kind of question. So Madhuri has this question on assignment 5. Assuming all I/O operations are overlap, what is the actual question? So can you look at the other thing?
This one?
Yeah, cool. This is 5.
Week 5.
Yeah. Okay. Week 5 assignment. Okay. Okay, so in the so there is a problem trying to open that particular question, so I can just answer it. What we mean by overlapped I/O operations. So typically, when we do an I/O operation, what we know is that you have a process which performs an I/O operation, and that process actually stalls until the I/O operation completes. Right. So when the I/O operation completes, then the process is actually woken up and goes to the ready state, and then starts to run. So when we actually talk about overlapped I/O operations, you could have multiple processes. All of them could have I/O operations at the same time, and these I/O operations can be serviced at the same time. For example, one I/O operation could be, let's say, waiting for a user to enter something on the keyboard, while another I/O operation could be actually waiting for some network data, or third I/O operation could be waiting for a disk to actually send a particular page to RAM. So all of these things are essentially overlapped, and can be done can be done in parallel. So it can be done in parallel because all of these devices are independent and are different, and therefore do not interfere with each other. So Vikas Kumar has a question on starvation. So starvation, essentially in the context of a process or processes and synchronization, occurs when you have one process which is ready to run in all aspects but is denied the particular resource. In case of scheduling, for example, it would mean that if you have a bad scheduling algorithm, or your scheduling algorithm is not designed in the right way, starvation would occur if you have a process which doesn't get the CPU to actually execute. So one example of when starvation occurs in processes is, let us say that you have a scheduler which looks at the highest priority process and then executes that. So essentially, this particular scheduler looks into your ready queue and it picks out the process which has the highest priority and then executes it. So this could actually lead to a starvation of low priority processes. So for example, let us say that we have three processes. Process 1 and process 2 has the highest priority, and process 3 has a low priority. So the scheduler will always pick the high priority tasks, that is process 1 and process 2. And let's assume that after they run, they actually come back into the ready queue. And therefore, it's either process 1 or process 2 that executes. Process 3 will never get a chance to execute, and therefore it goes into a starvation. So process 3 is essentially denied execution in the CPU. Sandeep Pandey, so he has a question between deadlock and spin lock. Okay, so deadlock and spin lock are essentially two totally different concepts. Deadlock, as we know, it deals with more than one process and more than one resources, and each of these processes are actually waiting for the other process to actually either return a particular object they are holding, a shared object that they are holding. So we had this entire chapter about, or entire lecture about the deadlocks, how they can occur and how they can be prevented. Spin locks, on the other hand, is used as a locking mechanism. So you could have spin locks in a mutex or spin locks in a semaphore. So what is a spin lock essentially? So there are two ways in which a mutex or a semaphore can be implemented internally. So one thing is that, for example, in a mutex, if you do not, if let us say you are trying to, you've written a program, and in that program there's a mutex lock, and you are actually trying to enter into a critical section, but unfortunately there is another process or another thread which is already present in the critical section. So in such a case, this particular process would be blocked, right? So this particular process would be blocked. Now, during the block state, there are two things that the process could do. One thing, it can actually go out of the ready queue and go back to a blocked queue, right? So on the other hand, what it can do is it can actually run a loop, continuously waiting for the mutex, continuously waiting to get the mutex, and when it gets the mutex, it would then enter the critical section. So you see that there are two ways to actually deal with the locking mechanism when a particular process does not directly get the lock. Either you could, the process could actually go from a ready state to a block state and remain in the block state until until the other process has come out of the critical section. While the second option is the process could remain in the ready state and continuously keep polling and trying to enter into the critical section. The second one, where the process continues to remain in the critical section, is known as the spin lock. So the advantage of the spin lock is that once the other process, the second process, is exited from the critical section, this process, because it is continuously spinning trying to enter, would immediately be able to enter into the critical section. On the other hand, with the first prior approach, the process goes from ready to block state, and therefore has to be woken up. It has to go back from the ready into the ready queue, and then therefore all of this would take quite a few clock cycles, and therefore it would actually be a delay. So we typically use spin locks when we know that a particular process does not have to wait for too long before it can actually obtain the lock. I hope this answers your question, Sandeep. So Smita has a question about what is a deadlock and what is a live lock. So I have not heard of a live lock before. Yeah, possibly that's a new terminology which I have not heard of. Okay, so Krishna Kant has asked this very interesting question about why is it not practical to use deadlock avoidance algorithms like Banker's algorithm? Can we calculate the number of maximum number of resources needed a priori? So in Krishna Kant, in many applications it may be possible to actually be able to calculate this. Things have a priori. So for example, in a very closed control system environment or an embedded platform where you know the processes which are going to be executing, and you also know that what resources each process is going to ask for, then in such a case you can actually use a deadlock avoidance algorithm like the Banker's algorithm. However, in more enterprise applications or enterprise systems, let us say a web server or let's say a banking software, you may have thousands of customers, you have very complex state and applications. Trying to make an estimate of this is of the requirements is very difficult. Therefore, in such cases, applying the Banker's algorithm would be very hard. Therefore, what is whenever if you're, let's say, building an operating system or very large applications, so you have to make a choice whether you actually want to have a deadlock avoidance algorithm or any other deadlock prevention mechanisms. So you need to take into consideration about what is the probability of a deadlock actually occurring. So one very simple thing is that if a deadlock actually occurs, the easiest solution is to just restart the entire system and hope that when the system actually restarts, then you would not get a deadlock anymore. Or this is a very guaranteed way to actually break the deadlock. So if, let us say, the probability of deadlock is say 0.001%, which is typically a very realistic number for deadlock occurring. So just restarting the system would be would not be too much of an issue, and you would not need to actually implement any of these Banker's algorithm or any of those sort of forms. Therefore, most commercial operating systems like Linux and so on would not actually do not actually have a deadlock prevention or avoidance techniques. However, if you have very mission critical applications such as say an operating system which is present in an embedded platform which is used say in a spaceship, then you may actually have to think more critically whether you want a deadlock prevention or avoidance application. So Android is Android an operating system. Android essentially runs over Linux. So the kernel itself is the Linux kernel. So Android, I would not call it as an operating system. So the kernel uses the kernel Linux kernel. So the features and everything of the underlying kernel is the Linux kernel. So therefore, Android, I would say, is built over the Linux kernel. Okay, so I would like to thank you all for joining into this session. It's been extremely wonderful to actually talk to you and answer all your questions. please feel free to email us or mail us in the forum if you do have any queries, any further queries. And for students who have actually taken the exam, and if you're interested to if you have done well in the exam and you actually feel that this operating system course has helped you a lot, and if you have done well in the exam, please feel free to let us know. You can always drop an email to us if whether you're interested in for an internship or something, and we can actually see whether we could work on this and help you actually educate yourself more in this direction. Thanks a lot for your time and listening to this lecture. Thank you.